Hello, this is Mike at Gamefromscratch, and welcome back to our ongoing LibGDX tutorial series. Today we're going to be starting a new multi-part series within the series, specifically covering 3D. It's not going to go into incredible depth because the reality is LibGDX itself isn't really that much of a 3D library. The functionality is all there, and the nice thing is it's provided in a nice cross-platform friendly manner. So it'll run on HTML5, it'll run on Android, it'll run on iOS, and it'll run on desktop, but ultimately underneath, it's actually using different systems. On on Windows, Mac, and Linux, for example, it's actually using the LWJGL library, which are themselves fairly compact layer over top of OpenGL. On the mobile systems on Android and iOS, it's actually running over top of OpenGL ES, which used to be for embedded systems. I'm not sure if that acronym still holds up now, but it's a somewhat stripped down version of OpenGL optimized for mobile deployment. With recent moves in the OpenGL world, they're actually getting rid of that. They're merging into one single version of OpenGL, but that's a conversation for a different thing. So know that there are slight differences, and then again, on the HTML5 platform, the underlying system is WebGL, which itself is a subset of OpenGL ES. So you have these three different systems across the different platforms, and they all work in a slightly different way. And the nice thing is, LibGDX takes care of that for you. It provides you kind of a common interface to write to with access to the underlying 3D. However, if you're going to want to use some stuff that's very specific to desktop or certain extensions, etc., you are losing other platforms. But if you stick to the standard stuff, it works cross-platform and it doesn't take a lot of work. Today's conversation is actually going to be fairly short. We're going to look at just creating a first 3D scene, get a cube up on screen, and then rotate a camera around it. That's all we're going to try and accomplish today. But it will introduce you to 3D itself. Now, the 3D graphics world, the underlying technology there is actually no different than the 2D. Those worlds merged a while ago. And when you're working in a 2D game, it's all really 3D and it's being faked for you. Now, the nice thing is LibGDX takes care of all that for you. So generally, unless you're doing stuff like front buffer, double buffering, shader programming directly, etc., you're not actually dealing with the hardware that much. When you're working in 3D, you get a little bit closer. You still don't have to fully understand how the rendering pipeline works, but it is there. So LibGDX is providing you some layers, so you don't have to do shader programming yourself, but you are going to be passing in some parameters to shader programming. I'll give you a quick overview of how the 3D world works and worked, so maybe it'll make a little bit more sense. It used to be back in DirectX 9 and OpenGL 2, maybe 3 first version, around that layer or that area, the 3D graphics world worked in something called a fixed pipeline. It actually made a lot more sense as a fixed pipeline, but it was a maintenance nightmare. The whole idea is if you wanted something in the world, there was a function for that. So you would call create light, create texture, create this, create that, create this. And as they added new hardware to each device, they had to basically extend this model. Now, they would essentially, your video card back in those days would have silicon in it to handle all these different function calls. So you could almost think of like a C function called get texture. Well, the driver itself would then have the function equivalent built into the driver, which then would have the equivalent pretty much built into the silicon. So for every new extension, there needed to be a mapping back and forth. This quickly became unwieldy, and we got lost in this world of extensions and extensions that worked on some devices but not others, and it created a very, very nasty kind of world. On top of that, the way that we got faster was basically by breaking things down into very small instructions that processed very, very fast. And this gave rise to the vectoring and shading units that are basically the fundamentals of 3D today. And the 3D world changed a little bit, and it went from this fixed function pipeline, which is to have all this different functionality built right in, to more of a shader programming pipeline. So what you do is you broke your program down into little bits of executable code that did all kinds of different things. So instead of like saying create light, you would actually have those as I guess you would have these little shader programs actually that would run for every single entity in your scene. And it sounds very inefficient, but the hardware was really fast. So you actually would run a pixel by pixel. As you were processing all the pixels on your screen, there would be a little program that would run for each and every single one of them. And that's how you would apply lighting effects, texturing effects, and even like the really basic things of 3D were actually done using vertex shaders, which is to say, if you have a dot in 3D space that's available here and you want it to be drawn on your space, on your monitor, that translation is actually done using a shader. Everything was ultimately moved into shaders, and that's part of the world now. Now, LibGDX itself hides you from this a bit, but you are going to be passing in parameters. When you're passing these parameters and you're passing them in to shader. It's being bound. It's bound attributes, bound properties, etc. So behind the scenes, if you ever want to look deeper, and I might actually cover this in a slightly later tutorial, there is ultimately a shader behind the scenes being populated. Nice thing is, again, it's taking care of it for you. So that's a little bit of the overview of how the 3D world works now. Let's jump right into an actual code example. Here I am. I'm at the standard starting. I've created a brand new project, and we want none of it. Well, actually, we want to clear the screen. But we're not using a sprite batch. Another thing we need to do now is also clear for the depth buffer, because we're actually going to be working in 3D here. So instead of just clearing the cover bit, you're also clearing depth buffer bit. And that's it. That's all we're keeping from before. So this is, here, let's switch this to black, because that bright red is awful. So this code is pretty common. This is Bitwise math. You may not be familiar with that, but you can use a Bitwise OR, and you're masking a whole bunch of different bit values together. For example, if you have a value that's, say, GL colored bit value is binary of that, okay? And then your GL depth buffer bit value is, let's say, that. So that allows you in one single number or one integer of space to have encoded multiple bits of data. So this bit and this bit set says, actually I should do it as a single bit. So there is your setting for, say, the buffer bit, and there is your setting for the depth buffer bit. What you're doing here is you're saying if this or this, that's what this bitwise or means. So at the end of that calculation, you'll end up with this value of that. So welcome to Bitwise Math 101. It's very simple. All you're doing here, this functionality here, is just so that you can have multiple flags, and it's almost always just used for flags, but it's having multiple flags within a single integer value. So if you think about it, there's 32 bits in a standard 32-bit integer, so you could encode 32 bits of on-off data using one value, as opposed to creating 32 different booleans, where if you keep in mind, a bool is actually not one bit in size. It's generally system dependent, which makes it either a byte or even 4 bytes or even possibly 8 bytes in size. Generally it's 1 byte. But this then, you can now, since each byte actually has 8 characters in it, you can store 8 times as much data as you could with a single bool. So, sorry, quick math instruction there. Let's get over that now. So when you see this, that's all you're saying is it's kind of confusing because you would think it would be and I'm not going to go into why that's confusing, but this is effectively what you're saying. You're saying, I want to set this property and I want to set this property, but you're using a bitwise OR to do it by saying, if it's got this value or this value, set it to true. So very, very basics of bitwise math, and that's what we're doing here. So all we're doing is really kind of basically telling GL to clear both the bit buffer and the depth buffer. Okay? So now let's actually get to work. I'm going to go ahead and introduce a whole lot of classes all at once, so I declare these variables here, and then we'll go through them as we get to them later on. So first thing we're going to need, actually I guess everything can be private, is a camera. Now you have two options when it comes to cameras here. You have orthogonal or perspective. Now the difference between those two is pretty much 3D. And mostly what you'd use a perspective camera for is a 2D side shot. There are occasions where you would use it otherwise, but the biggest difference is perspective camera fakes the way your eye works, because obviously you're looking at a 2D image that it's faking a 3D scene. But the way your eye works in the real world is as things get farther away, you perceive them as smaller. So when you create a camera that's a perspective camera as opposed to an orthogonal camera, as things in the scene get further away, they will be drawn smaller and smaller. So that is the difference between orthogonal and perspective. In reality, what it boils down to most of the time is you're working in 3D, you want a perspective camera. If you're working in 2D, you want an orthogonal camera. All right, so that's it. We'll create a camera like so. We're going to need a model batch like so. Now, a model batch is just like a sprite batch. Whole thing. Actually, I may not have explained what a sprite batch is, so I will actually explain this here. Um, there are expensive operations on a GPU, one of which is sending information in and out. So if you can take all of this data and smash it together into one piece, it's a lot faster to process. Well, when you're dealing with 3D, you're generally dealing with polygons, edges, shapes, textures, etc. And they all go together to make up a single model. And you can actually have multiple models all kind of thrown together in the same batch. Now, what this does is it turns pretty much a very complex scene into a single draw. You're basically saying, draw these 5,000 polygons. And the more you can put into a single batch within reason, the faster it's going to be. So by batching your polygons, it's just like batching your sprites. It performs way faster. And behind the scenes, LibGDX can do some optimizations for you. I think it does like hidden surface removal and such, so if it's not even visible, it'll be culled, so it won't be drawn, etc. But by using a model batch, it turns multiple draw calls into a single draw call, and that's something you always want to do when you can help it. It's sort of like how you can put a bunch of textures together to make a sprite sheet, like we've done a number of times in the past, while loading one single big sprite and then calling little bits within it. You're so much faster than loading each one separately. The same applies with polygonal data when you're working with a model like this, and that's effectively what a batch does. It batches all of the geometric data together into one single thing, and then does some optimizations behind the scene. Now, next up, we need a model builder. Now, a lot of times you probably won't need a model builder. Oops, there's ambiguous. Who else has a model builder? Oh, Sun does. Oh, probably a business model. Okay, anyways, we need a model builder just to build we're going to have a 3D cube. Model builder makes it easy for us to do that. So that's what that's ultimately going to be there for. On that same topic, we have a model being your 3D geometry, textures, etc. information. So basically, it's a 3D thing, and we'll call it's a box. And now you can have multiple instances of the same model. So if you have like a Jenga game where you're stacking boxes, you have one box model, but you have multiple model instances. Now, the model instance is literally an instance of the model. It will contain the instance-specific data like position, transforms, that kind of stuff. And then finally, we have an environment. An environment is, there's multiple. We want that one. This is some of the trickery that goes into making the shader that goes in behind the scenes, but more or less if you want to have lighting, etc., it's the environment that's going to be rendering it for you. Okay, so now we want to go ahead and create our camera in Create here. So first thing we do is camera equals new perspective camera. Okay, there's a couple of values here. First one is the field of view. Now, a field of view is kind of the visible cone you can see at. You've probably set a depth of field value before, or we did call DOF or POV when you play like a first-person game, and you know how you can set it to like a higher value and get more of a fish lens kind of effect, or you can set it very focused, like 45, and you only see what's directly in front of you. Well, that's what this value is. Basically, it's how wide-angled your camera is. We'll go ahead with a value of just say 75. That means you'll see 35 degrees to the left and 35 degrees to the right, or also known as 75 degrees. Oh, no, actually it's 30. Sorry, my math's bad there. So 32 and a half each way. And then next you just need your viewports float. I'm just going to use the graphics. And gdx.graphics.get height, like so. And that is our camera. This is our view into the world. It's actually going to be taken care of. A lot of times you would actually have to maintain a bunch of matrices yourself. Oh god, my brain's not working. Your perspective, your transform, and your world matrices. This is going to take care of all that. You don't need to worry about that. We'll probably cover it a little bit later on, but for now, don't worry. So next up, we have to position the camera. Now, I am just making up units here. Your world units are whatever the hell you want to make them. In my case, I'm going to just go with, I don't know, numbers. You could have it so that your world is in meters, in millimeters, in feet, in cubits, in whatever the hell you want. You just need to be consistent about it. like I said, I'm just completely making things up because I'm going to be creating my my thing at a 2 by 2 by 2. So I'm going to position slightly back from that. And then the position is a vector, it's 3 coordinates, basically your x, y, and z coordinate. Z in this case being into and out of the screen, with y being up and down. So we've got 0 for the x, 0 for the y, and 3. So we're 3 units back from the screen. And then now we're going to go ahead and, oops, my bad, dot set. There. All right. So we've positioned our camera. Now we want to look at something. And here we're just basically saying, look at the origin. All right, so we're 3 units back from the origin, looking at the origin. And finally, we are going to set near and far plane. This is, it's 2 sets of values. Basically, it's saying start, this is the closest bit of data to record, and this is the farthest bit of data to record. So like it's sort of like the range of your camera, as you will. This combined with your field of view go together to create something called your viewing frustum. We're not going to cover it too much, or at all, to be honest. But just you can set the near field to a very, very close value, such as 1 unit, and then the far plane is equals 300 units of random, and that's way high considering the units we're using, but it doesn't really matter. Again, you've probably set this in the in a game in the past, something along the lines of viewing distance determines how far out things render. Obviously, the further out you render, the more intensive it can be because there's more there. Also, it's going to fit your art style. You're probably not going to want people to see something that's far away if it's not actually in their best interest to see it. But that's what the near and far plane are setting. They're setting the view distances of your camera. And let's see, that's it. So now we create our model batch. And yeah, that was it. Unless you're dealing with a custom rendering context, that's quite literally all you need to do. And then our model builder, like so. Again, that's quite literally it. Now we want to go ahead and we want to create a box. You could create a box using vertices. It makes some ugly code. I have to do a lot more math in my head because then I have to create, let's see, a cube has 1, 2, 3, 4, 5, 6, 7, 8 vertices that I have to define, and I have to define the faces and such. Pain in the ass. So there's a bunch of helpers built into this model builder class to make different shapes for us. The first one equals, I'm not sure about the performance of this to actually use it in the real world. Oops. Model builder. So as you can see, there's a bunch of helpers here: create cone, create cylinder, create spheres, etc. We want to create a box, and our box is going to be 2 units by 2 units by 2 units. So that means 2 across, 2 up, 2 in. And then next up, we need to define a material for it. Okay, telesense, stop being useless. Let me close it down. Okay, so we need new material, like so. Material is what the surface is going to be covered in. We're just going to create a simple color attribute one, and that is quite literally using something called a color attribute. And then create diffuse. Diffuse is a scary word that isn't as scary as it sounds. You'll see there's these 4 different values being set there: ambient, diffuse, reflective, and specular. Diffuse pretty much you can be thought of as it's the color. I think diffuse comes from the word like diffusion, the way light displays across the surface. But ultimately, really all you're doing is you're setting the base color of something unmodified by light sources. So I'm trying to think of an example, something that is completely base color before changed. I don't really know. Okay, so anyways, all you're really doing is you're setting the color of this thing. And now light is ultimately going to affect it and change it at later time. That's what your ambient is, your ambient lighting. Reflection is the glossiness or the reflection from other surfaces. And specular is direct lighting, I believe. So that would be the result of the light being shined directly on the surface. And then there's normally emusive too, which is the ability to cast light, but that must be used somewhere else. All right, so we'll go ahead and create our diffuse here, and we'll just go ahead with color. I'll stay consistent. What did I do otherwise? Blue. What are you doing? All right, blue. Okay. So really, all we've done here, stupid thing. All right, I want that one. Is so we added a material to our surface, and finally, so that's the end of that one. We need to tell it what attributes we're going to be using. When you get into full OpenGL programming, some of these values, like this thing like color attribute, and then what you're about to see here saying position and normal, you're kind of telling the shader behind the scenes what's important here. And what's important to us here is position data and normal data. Position data simply tells it that this thing exists in 3D space. Here's the coordinates matter. Normal, a normal on the other hand is the direction something faces. So when you've got like a rectangle or such in 3D, it's drawn in a certain order, and the order that is drawn in, clockwise or counterclockwise, will determine which way, so from which direction it's drawn, because the surface isn't by default two-sided. So if you actually go through it and look back the other way, it's invisible. So the normal is actually important. You can think of the normal as a little dot. It's not actually a dot. It's nothing. It is completely nothing, but you can visualize it. And a lot of times in 3D applications, it's visualized as a little dot or a little arrow that comes out of the polygon or face that determines which direction you're pointing in. But a normal can just literally be thought of as which way is up or which way is out or which way, and that is what a normal is. A normal is the direction that a face is facing, so you know which side of it to be drawn. There are also settings you can say basically to say make faces two-sided, but if you think about that, when you do that, you're actually doubling up the workload, because if a polygon doesn't need to be rendered from both sides, you shouldn't. So anyways, so we need to set these two vertex attributes as attribute or attributes. Oh, sorry about that if I deafened you. I did not expect that one coming on. Okay, so vertex attribute usage dot. And as you can see, there are a number of the values set here. Again, this is really you're working with the shader behind the scenes without having to work with the shader. So you're passing parameters in are of importance. And like I said, you want position. And then once again, we're back to our Bitwise math. So you can put multiple values into a single variable here. And in this case, you want vertex attributes.usage.normal. So essentially, you're telling the 3D world that this thing has positional data and it has normal data. And if you don't, it won't render right. Okay, so again, nutshell, we just created this cube that's 2 by 2 by 2 in size. That is the color of blue, and that has positional and normal data. Again, normal being the direction that the face faces. And why are you unhappy with me? Oh, I have one too many. Okay, so that created our cube in 3D space, which for some reason I called box instead of cube, but we'll go with it. Now finally we need our, oh no, not finally, because our model instance. So like I said, the cube is thought of as an archetype. It is a model, 3D model with all kinds of information built into it. Like if I go here and I actually show you now, there are animations. You can get the animation, you can get the materials, you get the nodes that make it up, you can get the different sub-meshes, because a model can actually be made out of multiple meshes. Like you could have a body that's made physically out of a torso, arms, hands, shoulders, etc. Mesh parts, like you see, network of nodes, and each one of these has more bits in it, more bits. So if I go into mesh parts, it's a collection of mesh parts. So let's say get the first one, and then you'll see it has a list of vertices, indices, primitive types, which is generally a triangle strip or something to that effect. This is a hugely complex class, and it is also used once. So you can think of it like an archetype. So someone would design a single brick, but you would use hundreds or possibly thousands of instances of bricks, and that's what we need now. Is we need our model instance, and this is simply an instance of our box model class. It's a lighter weight too. The model class is quite large, whereas a model instance is very, very small. And we just create one using the class new model instance, and we pass in the box. So you pass in the model you want, and then you pass in where you want it. So we're going to create a box at the origin. That's what we've just done. We've just said we're going to create an instance of this model class at this position. Okay, and now finally we need our environment. Environment, super simple, equals new environment, like so. And we are going to simply set the ambient light color. This is to say we have some lighting in our world. Ambient lighting is lighting that is literally all around you. It's lighting without a direct source. You can also set positional lighting. It's a different thing, but we're quite content with ambient for this particular example. And to do so, now that we have our environment, all we do is go environment, and we do a set, and we're just setting an attribute. It's sort of like what we were doing earlier with the material, but in this case we're setting environmental attributes, and we are setting a new color attribute, like so. And now we want color attribute dot ambient light, comma, and now we're going to set the values for it. This is your RGB value, so if you wanted a red light, you would do 1,0,0, or 1.0, sorry. 0.0. In this case, we are going to do like kind of a grayish light. And the final value, I believe, is intensity, or we kind of, oops, no, we want that. One too many. All right. Intensity and light, and done. I think my bracketing is all right. Oh, no, no. I am missing. No, I did that wrong. Sorry. I don't need that. It is part of the color attribute value. I need another bracket here. There. All right. So what we just did is we just said add an ambient light. That means light from no particular source. It's just light that's there. Sort of, you can almost think of the sun as an ambient light, even though the light, it's a bad example because the sun actually comes from above you. It's got positional information. Ambient light is just light that is. So if you're in a room that theoretically had lights in the ceiling and the floor and just kind of all around, that would generally be your ambient light. Okay, so again, there are positional lights. We're not going to cover it in this particular tutorial, especially because I blabbered on longer than I extended. That's about it. All right, good. So now we're going to come back to our render call here, and now our render loop looks a little bit different than it did with the sprite batch. So instead what we're going to do, we update our camera, even though nothing's changed as of yet, like so. And then we want to render our world, and that is our model batch, just like we did with sprite batch before. This time instead we do model batch, and we do a render. You pass in the camera to render from, or to render using. Oops, sorry. Batch, model batch. Begin and pass in the camera to use for positioning, and then you go ahead and render each batch in it. So model batch dot render, and we want to render our model instance like so. This is just like when you're working with sprite batches, just instead of sprites you're dealing with models. And now you tell it you are done, like so. Now, one key thing I have not mentioned here is this class here is disposable. So if you do not call .dispose on it, you are leaking memory. It's just a thing I do. I'm leaking memory like mad in these examples. So again, remember, dispose of your stuff. If it's got disposable, get rid of it when you're done. Again, it's a program that runs and it ends, and it's not recurring, so there's really no issue with a memory leak in this case. But if you're obviously using models over and over again, dispose of them. Instance, I believe, is lightweight. Does not have. Yeah, there's no dispose on model instance. So your model, make sure you get rid of it when you're done. Same with your model batch. And I actually believe your model builder is disposable. So technically, I should actually get rid of that, right? Nope. No, it's not. Cool. All right. Okay, and I think that is kind of it for now. So I go up here and I shall run it. And if I did not screw up, we should see, oh, I screwed up. Find variable batch. Where did I use batch? Batch. So I should just click it. 27.9. Ah. My bad. model batch, and I did it right below. Model builder, so, and like so. All right, there you go. So if I've done this right, we should just get a blue cube in the middle of our screen. Boom, there you go. Welcome to your very first 3D application. It's being lit by an ambient light source, which is basically going to have very little effect on it, other than make it visible. And it is blue, and it's 3D. Now, that 3D doesn't seem overwhelmingly obvious because we're looking at it straight on. And let's do something about that. So, I think I missed my X. Let's stop our code. And now we want to go ahead, let's get rid of this guy for a second. And let's just wire it up so that our keyboard, when we hit the key, orbits our camera. And to do that, implement input processor, like so. Take my little light bulb and do the work for me. Thank you. Again, remember, input processor, we now need to register it. So gdx.input.set processor, or set input processor, this. Like so. So now we're just going to do it. We'll do it each time the person presses the key down. Yeah, that sounds good. Okay. So there, we handled a key. Deal with it. So let's check our key code. If key code equals keys dot left. Yeah, it works for me. So if you press the left arrow, why are you all pissy? Let's see, what does it want? All right. Left arrow, then we want to orbit the camera. So we're going to use the camera, and there is a nice little method in called, so you can rotate using quaternion, which is, how do I explain this one? You can rotate in 3 dimensions with like X, Y, and Z around axes. So you basically, when you say I'm going to rotate 30 degrees around the Y axis, that's axis-oriented rotation. The problem with this is there's actually a phenomenon called gimbal lock, which is you can rotate to a certain point, and then the mathematics just get really screwed up. The matrix mathematics behind the scenes just can't handle it anymore, and it goes spinning off into space. A quaternion is a mathematical equation which is way beyond my ability to define. I can't even pronounce it, so that's where we start. But it's got a 4th dimension that makes rotating arbitrarily about any axis possible. So you generally will actually use them when you're dealing with non-axis oriented rotation, so non-straightforward. So if you're rotating around 2 or 3 axes at the same time, is it quaternion? Quaternion? Anyways, that's what you use. In this case, though, we're going to go ahead and just define the axes that we want to rotate around. So first thing is first, we define the axis. So we are going to rotate around the first value is the point to rotate relative to. So this is the center point of your rotation. So we're orbiting the center of the world, like so. And then the second value is the axis to rotate around. And this is represented again as a vector. In this case, you're telling it which axis to handle. Now we want to rotate around the y-axis. So all you do is you set 0, 1 for y, and then 0 for your z, like so. Didn't do that. Okay. Now, I had to point another thing out. Like I didn't call dispose again. I am doing something very bad here. Very, very, very bad. Be aware of that. I've covered this a couple times in the past. This is horrible code. This using a new each time someone presses a key. Vector 3 is a very small class. It might take up 30, 40 bytes tops, and that's probably being really pessimistic. It's not a really big class by any definition of the word. But creating a new one, or 2 actually, every single time the user presses a key is very bad code. However, it's a lot easier to read and understand the code, which is why I'm leaving it as it is. But I shall comment. In the real world, do not create new variables over and over. Create a temporary static member instead. And what I mean by that is what you would probably want to do is create even if you called them temp1 and temp2, create two member variables of your class and reuse them for vector mathematics like mad. Because then you have one allocation and you use it over and over again. And the key thing is you are not going to kick in the garbage collector, and the garbage collector is not your friend. So you do not want to create a whole bunch of junk, because then it will kick in the garbage collector and then it will slow your code down. So bad. Do not do this. But when you're trying to make code legible, do it. That's kind of all I got to say. And then finally, the last value is the degrees to rotate by. So what we are doing here is we are going to rotate the camera. Oh, I am calling. That's why it's all mad at me. Sorry. Ugh. So we are calling cameras rotate around. We are rotating around 0, 0, 0 in 3D space. We are saying we want to use the y-axis. So saying that the rotation is along the y-axis, and it is 1 degree. So each time you press the key, we will rotate by 1 degree. Now, through the magic of cut and paste, we shall now have the right, and we're just going to go the opposite direction. Okay, so now in theory, when I run this, there we go. If I press my arrow keys, each time I touch it, there you go. Now, I'm going to pause here, rotate it at about, I think that's 45 degrees. Right there. Now this is where your perspective comes in. See how your front edge, and I'm holding my fingers in front of the screen, which does not help you at all. Notice the back line of your edge is it's much smaller than the very closest to you. That is the effect of your perspective camera. If you did not have a perspective camera, this back edge here and this front edge here would actually be the same size. Again, when you're dealing with, and see here, huge, small. But that's how your brain works. In 3D, you think further away things are smaller. So again, when you're working in 3D, 95 times out of 100, you're going to want to use a perspective camera. Or I guess that's 19 times out of 20. Either way. So that's it. That's your very first 3D program in LibGDX. We'll do a quick recap from the very start, but we're going to follow on a little bit more. There's not actually a ton of functionality in LibGDX itself. There is, however, the model instance stuff that we're going to get into. So far, we've just used a very simple one. We used a model that we've created ourselves, this box. We also could have defined one ourselves, like a cube or whatever, using the Vertex information. However, what most people, 95% of games, are going to do is actually import that data from a 3D application such as Blender, Max, Maya, or whatever. And that functionality is built in. There's something called the FBX importer. You can then use it and have animated 3D textured models easily used. And that's what we're going to cover next. And then, kind of, to be honest, that's about it for 3D for now. But here you saw, just to get the basics down, how things work, how to position the camera, perspective versus orthogonal, how to set the environment to get the lighting and such in your world, model batch to batch up just like you use for sprite batch, but the 3D instance of it. So again, here let's do our quick recap. So we implemented the input processor so we can handle keys. We created a perspective camera, a model batch, a model builder, a model instance, and an environment. Again, that's the camera. A perspective means as it gets further away, it's going to get smaller. Model batch is an optimization thing for batching up a bunch of geometry, textures, etc. To make it as little calls as possible in the GPU as an optimization thing. Model builder we use to create our model using its built-in create box function. And then the model itself is the 3D information of the box that we actually created, or it'll be what you load from Max, Maya, or whatever. But the model is very fat. It's got all of the geometric information, the texture information, etc. Now the instance, on the other hand, is just the positional information, the spatial information for the model. Lightweight class, and this is what you use when you're creating lots of them. So the model is the prototype, and then the instance is, well, the instance. And then finally your environment is for your lighting that affects all the objects in the scenes. I guess, yeah, I should point that out, because you can actually apply these things at the model level, but this is environmental stuff is global, so it'll affect all of the things rendered using that same environment. Okay, so then we went ahead and created our camera, positioned it, so we moved 3 down the the z-axis or in or out of the screen. We then set it to look at the origin. We set how close it will record information and how far it will. So these two combined with the depth of field or perspective degree, those work together to create your view frustum if you really want to look that up. Next up, we created our model batch. Our model builder created an instance of our box, made it blue, and told it that we have positioning and normal data. Again, this is used for the shaders behind the scenes. We created a model instance at the origin of our box. And we created our environment. We set the ambient light to a gray, full intensity light, and wired up our input processor. And oh, you know what? I made an error here. Oops. We set our environment. Never actually used it. Oops. Sorry. That's important. When you're passing in a render, the environment actually needs to be passed in as well. It's not going to have a huge effect, but it will actually now be better lit. There we go. Sorry about that. So as you can see, it's not really mandatory to call that one, but I didn't call it at all, which is a mistake. All right, so continue on. Now that I've corrected that mistake, sorry about that. In our render call, which is our draw call being called every frame, we clear the color to black. We tell it that we're clearing both the color bits in the buffer as well as the depth buffer. Then we update the camera's position, which we are changing here. So that's what causes this change to actually happen. So if you did not make this call, this would do nothing. Then we say that we're going to use our model batch, and when we start it, you pass in the camera to use. So obviously this will also immediately tell you that it's easy to have multiple cameras, just passing a different one to the different model batch. It's also possible to have multiple environments, because obviously you pass them into the render call. To the render, you pass in the model instance. There's also, let me show you quickly, batch dot. So you can pass in a list, provider, or a single. So in this case, we're passing in a single. But if you had any data container that implements interval can be passed in. So generally, that's what you would do. You wouldn't call render for every single model instance. You would have a data type or something of the models to be drawn, and you just pass it into a single call. End result's the same. It just probably calls them in a loop behind the scenes, but since we only have one, we call it this way. But often you would use a container of some kind and then pass it in. And then finally, we tell the batch that we're done. And then here we're simply orbiting around the axis if they press the left or the right arrow. And that's it. That was a basic 3D program in LibGDX. Like I said, the next part we'll cover, we'll look at exporting from Blender and into LibGDX, and show you how to draw the model in the game, and a little bit about how to play animations. Hope you enjoyed that. Thank you very much. Bye.